So in this video, we start considering the last topic of this course, which is ergodic theory. Ergodic theory is seen from the point of view of spectral theory. So from the point of view of spectral theory, ergodic theory is about the following question. I have a bounded linear map acting on some Banach space. Let's say, for the sake of simplicity, that this is a contraction. And the question I'm asking is, do the powers of T converge in an appropriate sense? Okay, now why do we want to study this? So let me give you motivation. First of all, the key motivation of ergodic theory coming from where it is typically applied, and second of all, maybe a motivation that is more internal to spectral theory. So from a point of view of application, we often take X to be either a space of continuous function over some space of variable omega, some metric space of variable, or an LP space over some measure space of variable omega. And when we deal with the space of continuous function, we talk about topological dynamics. When we work over an LP space, we talk about measurable dynamics. And the operators we consider in both cases are composition operators, so maps that sends a function f to the function which evaluated at a point omega is just the function f evaluated at a point phi omega so that's for every f in my space X, for some transformation phi of the underlying space of variable. And that phi can be continuous in the case of topological dynamics, or it could be measurable in the case of measurable dynamics. There's also dynamics within the context of spaces of holomorphic functions in complex analysis, and then you might want to map phi to be analytic. It depends on the context, but typically you study composition operators. And the typical result in ergodic theory is a result that will tell you that the powers of this operator converge, but maybe not just in the sense of plain convergence in the norm of X, but converge if you consider certain convex combination of the powers, and convex combination such as the Chezar averages, where you just give weight 1 upon n to the first n power of the operator. So typically this will converge as n goes to infinity to a number, to the average of the function omega. Let's say in the context of measurable dynamic over a measure space omega that has finite measure, you will get exactly this, d mu omega, and you will get that at every point, or almost every point, omega prime. Almost every omega prime in omega. So this is interesting to stop and think about what this result means. This is often referred to as the Ergodic hypothesis, because it was first hypothesized in statistical mechanics that systems will tend to behave this way. So what is Tj of f really at a point omega? It's f of phi j of omega, where phi j is defined inductively by phi j of omega equal phi j minus 1 of phi of omega for every omega and capital omega. So what we are doing is that for a fixed individual, we're looking at the orbit obtained by applying to that individual point the transformation phi repeatedly, and then we average over the values of f at this particular sequence of points, and this average over time, if you think of applying phi at each point of time, converges to the average of a space of the function f. So it's really telling you that you can understand the average of f over all possible value of omega by just looking at the orbit of a fixed omega prime. So the orbit of a fixed omega prime, the nature of the transformation phi is such that the orbits are sufficiently descriptive to tell you something about the global average of f. So this is the idea of how ergodic theory is typically applied in order to understand this time averages converging to space averages in the language of statistical mechanics, but it has application to all sorts of other parts of mathematics. I mean, in geometry and number theory, there's various questions that reduce to understanding convergences of such convex combinations of the linear maps that arise from transformation that are nonlinear on this underlying space of variables. So this is the motivation coming from application, but we're going to prove results such as this typical result of ergodic hypothesis through a purely spectral theoretic approach about understanding convergences of convex combinations of powers of bounded linear operators. And for us, this is also an application in itself, because if T happens to be of the form 1 minus S, and S is a compact operator on my Banach space, then these averages, or the powers themselves, or whatever, in whichever sense the powers of T converge, they would have to converge to an operator P, in an appropriate sense, that is such that T of P of X is P of X for all X. Obviously, because the limit of the T, or the limit of the Tn, or the limit of the Tn plus 1 has to be the same thing. So this P will typically be the projection onto the null space of I minus T, which is the null space of S. So Fredholm's theory has taught us how to factor out the eigenspaces corresponding to non-zero eigenvalues of a compact operator. Now, ergodic theory gives us an answer to the question, can I factor out the null space corresponding to the element 0 in the spectrum of my compact operator? So if you can put together both Fredholm theory and ergodic theory, you get a full decomposition of your space into eigenspaces, just like we had in the spectral theorem in Hilbert space theory. So this is somewhat an internal motivation for us, but it is also part of the proofs of the general theorems of ergodic theory seen from the point of view of spectral theory that can then be applied in specific instances such as the one discussed in 1 to get more concrete result like this one. This one is more concrete because you prove convergence of these averages of the power to the projection onto the null space, but then you determine that this null space has to be one-dimensional and that the projection has to be given by this map, the average of F. We'll prove a theorem of that nature down the track. But as we get started, the first thing we should see is the quintessential example of an ergodic theorem, and that's a theorem due to von Neumann about contractions on Hilbert spaces. Let's start with that. So we're going to start this chapter by proving the quintessential example of an ergodic theorem. That's von Neumann mean ergodic theorem, works in Hilbert spaces for contractions, and what it tells you is that the Cesaro averages of the powers of any Hilbert space contraction converges in what's called a strong operator topology to the projection onto the null space of identity minus T. What we mean by the strong operator topology is that the convergence of this sequence of operator doesn't happen in the operator norm, but it happens when applied to any H in the underlying Hilbert space, capital H. Now the proof of the theorem will be split into two lemmas and then the main proof. The first lemma is a characterization of the null space of I minus T, and we get this neat little characterization which is the same for T and for its adjoint T star, so it gives us the fact that the null space of I minus T and the null space of I minus T star have to be the same thing. And then from this lemma, we get that the Hilbert space H has to split into the null space of I minus T and the closure of the range of I minus T. So we have this nice null space range splitting, and from there we prove our theorem. Now, in both parts of the chapter 14 on ergodic theory, we will do things in this way. We will first prove a theorem in Hilbert spaces using all of the techniques that we have at our disposal in Hilbert spaces, and then we'll see how such a theorem can be generalized to certain Banach spaces, typically reflexive Banach spaces. And this generalization for von Neumann theorem is due to Yoshida in 1938, and we'll see that theorem after. Okay, so let's start with the proof of lemma 14.2. One direction is easy. If I have H in the null space of identity minus T, then what can I say about H inner product with T of H? Well, T of H has to be H, so this is the exact same thing as HH, which is the norm of H squared. Okay, so that's fine. And then what about the other direction? So let's take an H in capital H and assume that the norm of H square is the inner product of the norm of H with T of H. Okay, then what happens for such a thing if I look at H minus T of H? I want to show that this has to be 0. And if I square that and I expand the inner product, I get norm of T of H square plus norm of H square minus 2 times the norm of H T of H. But the norm of H T of H is the norm of H square, so I get minus 2 times the norm of H square, so I get the norm of T of H squared minus the norm of H square. And T is a contraction, so this is smaller than norm of T minus 1, sorry, norm of T squared minus 1 times the norm of H squared, and norm of T is smaller than 1, so this is smaller or equal to 0, therefore it has to be 0, and therefore H has to be T of H. And that's it. That concludes the proof of Lemma 14.2. Okay, so the proof 14.3 now, what we need to show is that the perp of the null space of I minus T is the range of I minus T, or the closure of that, right? Because we know that H can always be split into the null space of I minus T and its complement, which is its perp. And so if the perp is exactly the closure of the range, then we will be done. So there's two inclusions to be shown, that the closure of the range is in the perp and that the perp is in the closure of the range. So let's go with this inclusion first. Let's take an element F in the null space of I minus T, and let's take a, say, G in H, and H equal identity minus T applied to G. So what happens if I take the inner product with F and H? I get that it's F I minus T G. Okay, and now this means that I have I minus T star F applied to G, but remember that the null space of I minus T is the same thing as the null space of I minus T star. That's from Lemma 14.2. So from Lemma 14.2, I get that this has to be 0. And therefore, H has to belong to the perp of the null space of I minus T. So we have that the range of I minus T is included in the perp of the null space, and because a perp is always closed, I can take the closure and it would still be inside that perp. So I've proven one inclusion. Now let's have a look at the other inclusion. What if I have an F which is in the closure of the range perp, and then all I have to show this time is that this has to be into the null space of I minus T. If I take a G in H and I look at F applied to I minus T of G, well, because F is in the perp of the closure of the range, this has to be 0. But this tells me that I minus T star applied to F comma G has to be 0. And so what can I say from that? I can say that the perp of the closure of the range has to be included in the null space of I minus T star. But we know that this null space is the same thing as the null space of I minus T by Lemma 14.2. So we've proven that the perp of the closure of the range is in the null space. Therefore, if I pass to perps, the perp of the null space is included in the closure, in the perp of the closure of the range. But we've seen that when you take perp twice in a Hilbert space, you get your subspace back. And that concludes the proof of Lemma 14.3. So now we know that whenever we have a Hilbert space and a Hilbert space contraction T, the space splits into the null space of identity minus t and the closure of the range of identity minus t. So we're going to use that and prove von Neumann's theorem. Okay, so we have the splitting of H into the null space of I minus t and the closure of the range of I minus t. So let's have a look at this different component. Now, if H is in the null space of I minus t, then the theorem is very easy to prove, because for every n in n, we have that the Chazaro averages of tjh, well, tjh is just h for every n, so this is just equal to h, which is equal to p of h, because if you're already on the null space and you're projecting, you do not change anything. So this is true for all n, so of course this is true for the limit. Now, what about a g in the range of I minus t? Not the closure, just the range itself. Now, for such a thing, I have that for all n, in n, 1n sum j equal 1 to n of tj of g. So let's take an h in capital H, such as g is I minus t of h. This is 1 upon n times the sum j equal 1 to n of tj minus tj plus 1 of h. And now these sum telescopes, and so what we are getting here is 1 upon n times h minus t to the n plus 1 of h. And now notice that our operator t is a contraction. So this is smaller than 2 times the norm of h divided by n. And that goes to 0 as n goes to infinity. But 0 is certainly the projection of g onto the null space, because g is in the perp of the null space. So we've proven the result for an element of the null space, and we've proven the result for an element of the range. We just need to get to the closure of the range now. So if I take an h in the closure of the range, okay, I can give myself an epsilon, and I can give myself a g in h such that, a g in the range of I minus t, such that the norm of g minus h is smaller than epsilon. And then what happens when I look at 1 upon n, for any n, okay, non-zero, when I look at 1 upon n times the sum j equal 1 to n of the tg of h, what is that? This is smaller than 1 upon n sum j equal 1 to n of tj of h minus g plus 1 upon n sum j equal 1 to n of tj of g. Now we already know that this part here is smaller than 2 upon n times g. And what about the first part? Well, it's smaller by triangle inequality than 1 upon n sum j equal 1 to n of t to the j applies to h minus g. And so this whole thing is smaller, because t is a contraction, than 2 upon n g plus epsilon, which tends to epsilon as n goes to infinity, and epsilon was arbitrary. So this has to tend to 0, which is p of h, because the perp of the closure of the range is exactly the null space as n goes to infinity. And this concludes the proof of von Neumann mean ergodic theorem, quintessential example of a ergodic theorem. Now, this is all good and well, but if we look at this proof, we've certainly used very Hilbertian techniques, right? We've used the fact that we have perps, every closed subspace has a complement that is given by the perp. We always have the projections, and we've used inner products in order to characterize null spaces. So all these techniques will need to be adapted if we are to work in more general Banach spaces, which is what we're going to do next, through the Yoshida version of von Neumann mean ergodic theorem that works in general reflexive Banach spaces.